Hey everyone, welcome back. Today we're tackling an explainer on something that sounds super intimidating, but is actually incredibly cool once you get the hang of it: thermodynamics. We're going to take this complex academic topic and just totally demystify it. We'll be pulling straight from actual university lecture notes, scientific diagrams, and exam materials to visualize exactly how the physical universe operates.
But hey, before we jump right into the heavy math and the strict laws, we kind of need to put on the right pair of glasses. You see, physicists essentially look at the universe through one of two lenses. On one side, we have the macroscopic approach. Think of this as the big picture view. It's where we look at the overall behaviors of a system, stuff we can easily measure, like pressure, volume, and mass, without agonizing over every single individual molecule. Then, on the flip side, we have the microscopic approach. This is super zoomed in, calculating the constantly changing speeds and energies of literally billions of tiny individual particles. Now, for most applied engineering, and definitely for our journey today, we are going to stick to that big picture, macroscopic view. It just makes things so much easier to grasp.
So here is our quick roadmap for today's explainer. First, we'll define thermodynamic systems. Second, we'll cover the laws of energy. Third, we'll look at engines and refrigerators. And finally, number 4, understanding phase changes. Let's get right into it.
Part 1, defining thermodynamic systems and setting our boundaries. Basically, absolutely everything in the universe can be boxed into one of 3 thermodynamic systems, and it's entirely based on what is allowed to cross its borders. First up, an open system. This one's easy. Both mass and energy can freely flow in and out. Then, we have a closed system, which is a bit more strict. Energy can cross the boundary, usually as heat or work, but the mass is completely trapped inside. And finally, an isolated system. This is the ultimate vault. Absolutely nothing, no energy, no matter, can enter or leave. Just look at how this plays out in the real world. Think of an open jet engine. You've got fuel and air rushing in, exhaust blasting out, and energy transferring everywhere. Now contrast that with a closed system, like a sealed piston cylinder. The gas inside is totally trapped, right? But you can still heat it up or compress it, which transfers energy. And then you have your completely sealed, isolated box. It's totally cut off from the surrounding environment. No heat in, no air out. The whole shebang is locked down tight. Moving on to part 2, the laws of energy, the cosmic rulebook. All right, the first law of thermodynamics, think of this as the universe's absolute no-nonsense accounting department. It clearly states that energy cannot be magically created out of thin air, and you definitely can't destroy it. It can only be transferred from one place to another or, changed from one form to another. If you pump heat into a system, that energy has to go somewhere. It either does mechanical work, or it just increases the internal energy of the system itself. You simply cannot get something from nothing, period. Now, if the first law tells us about the sheer quantity of energy, the second law is all about the direction it travels. Specifically, the Clausius statement of the second law dictates the natural flow of the universe. It explicitly tells us that heat will always naturally move from a high-temperature medium to a low-temperature medium. It's exactly why that hot cup of coffee you forgot about on your desk always cools down. Its heat naturally just wants to escape into the colder room. Section 3. Engines and refrigerators. This is where we start manipulating nature. Okay, so knowing what we literally just learned about the second law, we've got a really fascinating mystery on our hands. If heat universally and naturally only wants to go from a hot place to a cold place, how on earth does your kitchen freezer stay completely frosty when the room around it is warm? Seriously, shouldn't the heat from your kitchen just constantly rush in and melt your ice cream? To figure that out, let's first look at its exact opposite, a heat engine. A heat engine perfectly obeys those natural laws. It steals heat from a really hot source, uses some of that thermal energy to do actual mechanical work, like say turning the wheels of a car, and then it just naturally dumps the leftover waste heat into a cold sink. It relies entirely on that natural downhill flow of heat we talked about. But here's the wild part. A refrigerator, it's literally just a heat engine running in reverse, because we are trying to force heat to travel backward against its natural flow. Literally pulling heat out of the cold freezer and shoving it into your warm kitchen, the universe demands a toll. And that toll is external work. You actually have to plug your refrigerator into the wall to provide the electrical work needed to forcefully push that heat uphill, so to speak. It doesn't happen for free. So how do we actually force this unnatural heat flow? Well, it all comes down to a really clever 4-step mechanical cycle inside your fridge, using the fluid called a refrigerant. First up, the compressor grabs that refrigerant vapor and basically cranks up its pressure and temperature. Second, it flows through the condenser coils, those hot grates on the back of your fridge, where it actually releases heat out into your kitchen. Third, it slams into the expansion valve, which causes this sudden massive drop in pressure, instantly chilling the fluid to freezing temperatures. And finally, this freezing liquid passes through the evaporator inside the fridge itself, absorbing the heat right out of your leftovers before cycling all the way back to the compressor to do it over again. It's brilliant.
Section 4. Understanding phase changes. Welcome to the real world of steam. In the engineering world, property tables, often called steam tables, are absolutely vital. Honestly, university exams usually rely on massive, terrifying walls of these numbers. But if we extract just 3 tiny rows from the saturated water tables, it gives us a wonderfully simple trend. We all know water boils at 100 degrees Celsius, right? Well, actually, scratch that. That's only true at standard atmospheric pressure, which is roughly 1 bar. Notice that at much lower pressures, like say 0.12 bar, water actually boils at just 50 degrees Celsius. No way, right? The rule is simple, but it is absolute. As pressure increases, the boiling temperature increases right along with it.
And this specific diagram maps out that exact relationship beautifully. That curved line creeping upward, it marks the precise saturation points. It shows us the exact combinations of pressure and temperature where liquid water actually begins its phase change into steam. Above that line, you've got superheated vapor, below it, compressed liquid. These diagrams are essentially the ultimate cheat sheets for engineers who design things like boilers, massive turbines, and power plants. Let's wrap up with this final thought, pulled straight from those university notes. Any device that violates either the first or the second law of thermodynamics is called a perpetual motion machine, which is a polite science way of saying it's impossible. While human engineering is incredibly clever, these thermodynamic laws remain the absolute, unbreakable boundaries of our universe. They govern every single machine we build and every natural process we observe. So the next time you hear your refrigerator humming in the kitchen, you'll know exactly what's happening behind the scenes. But it really does leave you to wonder, what other invisible, totally unbreakable cosmic rules are secretly running the appliances in your home right now?